Okay. So we'll look at the areas. So the area of A1 is 40 by 100, so it's 4,000 square millimeters. Area 2 is 20 by 200, so that's the same. Area 3 is 20 by 160, so it's 3,200. And we're going to need to add those up for later. So 4 and 4 and 3.2 is 11,200 millimeters squared. Okay, the y's we already have there. So the first one was 20, the second one 40, the third one was doesn't mean anything. So A times Y, if you multiply those out, you get 80,000, 560,000, and 800,000. Okay, so if you add those up, you get 1.44 by 10 to the 6, or just 440,000 square millimeters. Okay, cubic millimeters. So the Y bar is this one divided by this one. So if we work that out, it comes to 125 millimeters. Okay, so it's right in the middle, or it's close to the middle. So it's here. Okay, that's such a bad sketch. I'm going to draw that sketch again. Sorry. Really crap. So let's get rid of that. Okay, so we do it properly. Slightly better. Okay, so this thing is 125 from the bottom. So it's referred to as ZZ in the question. So that distance there is 125. Now the whole thing is 260. So the distance from the top is 135. So 125 plus 135 is 260. So it's nearly in the middle. Okay, so the long, sort of thinner part at the top is roughly having the same effect as the short, thicker part at the bottom. So it's nearly in the middle. So that means if it's nearly in the middle, it means that the top and bottom stresses will be roughly similar. It won't be the same. Okay, so based on that diagram there, just a quick poll. If I have a bending moment, if I calculate the bending moment and I work out the top and bottom stress at some point in the beam, obviously one is going to be tension and one is going to be compressive. But which one is going to be higher in terms of numbers? Is it the top A or the bottom B? So which one is it? Okay, I'll stop that one there. We might try it again in a sec. So let's just remind ourselves that stress is equal to my over I. So the I value is constant. Okay, the bending moment at some point we'll say is fixed. So the only thing that changes is Y. Okay, so at the top surface here, Y is 135, and at the bottom surface, Y is 125. So we'll try that question again. So A is the higher stress at the top, B is the higher stress at the bottom. Let's go again. It's only based around Y. Okay, let's see what happens. We still have people saying both ways. So let's finish out the calculation. So we'll stop the poll there, and we'll carry on. Okay, so the next thing we have to do is to get the I value for the section. And the way we're going to get the I value is we're going to get the I value of each of those little rectangles about its own center. And then we're going to transfer that to the neutral axis using the parallel axis theorem. So for each one of those little centers, I is BD cubed over 12. Okay, so I won't get you to do it out. I'll just put the numbers in here. So let's just extend the little table down. Okay, so we're going to need a few little values here. The first thing we're going to need is I of the rectangle, which is BD cubed over 12, and that's millimeters to the fourth. Okay, then we're going to need the distance from the centroid to the center of the section. So the centroid is running out there. So we need that distance. Okay. So, okay, if you work out BD cubed over 12 for A1, it's the breadth is 100. The depth is 40. And that works out as 53333. Okay. If you do the same thing for the middle bit, the breadth is 20. The depth is 200. And that works out, it's going to be a much bigger number. That's going to be 13.33 by 10 to the 6 millimeters to the fourth. And the top one, again, the depth is small and the breadth is large, so it's going to be a smaller value, and it works out at 106.667. Okay, so we can't add those because they're not about the same axis. So the next thing we need is the distance from the center of the section to the centroid. So in this case, if that's 125 from there to there, then that would be 105 as it's from here up to here.
Hi, Barry.
Yeah.
For Y, a lot of us got 128.57 instead of 125.
I need to just turn the. Sorry. Maybe. Yeah. Let me just check that again. Where do we get it? So let's see. Did you get the two big numbers there? Did you get 11,200 and 144?
Yeah, we both. Okay. Yeah, we got that.
Okay, I'm going to blame my Apple calculator here on my iPhone if that's the case. Give me a sec. So I was doing this out this morning, and I knew it was a bit too much of a round number to be. I knew it was too good to be true. 144,000 divided by 1. Sorry, yeah, 11200. Okay. Right, you're right. You're right. Okay, so let's change that. Okay. 128.57, isn't it? 128.57. Okay, so that means thanks for that. That means these values are correct. Actually, so it's one thing about these questions that there's two kind of things that makes them difficult. One is to figure out how to go about the thing, and the other one is that the numbers are kind of fiddly. So these values now are going to be different to what I had. So, okay, so the first one, if that's 128, okay, here, use the thing. That, get that. So if that's 128.57, then the other one is, so that minus 250. 60, is it? 60. 131.42. Okay, so still we have this thing that's nearly in the center. Okay, so this is not 105 then, this is, so it's 128.57 minus 40, sorry, minus 20 minus 100, so it's 8 point, sorry, it is 128.57 minus 108.57. Okay, the center of this guy here is 240, it's 140 up from the base. And this thing is 128.57, so the distance is a little small. It's 11.43. And then the last one, so the center of the last shape there is 250 up, and that's, so 250 minus 128.57 is 121.43. Okay, so the I values we have there are the I values of each of those rectangles about their own center, and we need to translate them to the I value about the centroid. So I'm just going to rub out some of the gunge in the middle there. So if we have our line coming across, okay, basically the I value of, let's say this, the first one here, the I value of that shape about its own center is relatively small, but the I value about this point here is going to be bigger, and it's going to be its own I value plus the area times that distance squared. Okay, so it's going to be, so we'll just keep going with the table. So we'll say A into y minus y bar squared. So that would be 108.57 squared times the area, which is 4,000. It's 47.15 by 10 to the 6. And if we add these two together, you get the I of that shape about the centroid. And that would be, it's not going to make much of a difference, 5333333. 47.68 by 10 to the 6. Okay, for the second one, we have 11.43, so it's very close to the center. So that multiplied by the area is 522,580. And again, we add this one and this one, and we get 13.86 by 10 to the 6. Okay, so the bit at the bottom has a bigger effect because it's further away. The middle bit is kind of straddling it, so it's got a slightly smaller effect. So the last one here, the distance is 121.43. So multiply that by itself and then by the area, and we get 47.18. Sorry, 6. And if we add those together, So this one, it's going to, again, it's going to make almost no difference. 47.29 10 to the 6. So we can add all these three together at the bottom line, and we get 47.68 plus 13.86 plus 47.29, 108.83. Okay, so you can see the I value of the bottom part and the top part are more or less the same. They're more or less the same distance from the center, okay? And they have roughly the same I value. And then the I value of the middle bit is, because it's not as far away, it's smaller. So if we add those together, we get that, okay? So that's the I value. So that the process is, if you kind of follow these processes, if you go work your way down this table here, you can get the answers fairly straightforwardly, okay, although it's a little bit messy. And that's where doing these things on a spreadsheet is actually quite useful. So that's why we'll get you to do some more homework using this kind of stuff in a little while. Okay, so that's the I value. So the question, so the part A of the question was actually that one there, to get a Y bar. Part B was to calculate the I value, and part C was if it was a 2-meter beam. So it was a cantilever beam, and it was 2 meters in length, and it had a 20 kilonewton load. That's fixed at the wall. Okay, so it's a cantilever. So if we sketched out the bending moment diagram, would look something like that. Okay, and the bending moment at the wall is just the force by the distance, which is 40 kilonewton meters, 40 by 10 to the 6 Newton millimeters. So that's going to, that beam is going to bend downwards. Okay, so the beam is going to bend down in that kind of a shape. So we have tension at the top, compression at the bottom. Okay, so the question was asking us what was the maximum tensile stress. Okay, so we know it's going to be at the wall, because that's where the maximum bending moment is. And we also know it's going to be at the top surface. So at the top surface, the Y value we want is this guy here, 131.42. Okay, so M is 40 by 10 to the 6. Y is 131.42. And the I value we have there, so top stress there is My over I, which is 40 by 10 to the 6 by 131.42 divided by 108.83 10 to the 6. That works out at, okay, by the way, if you want to follow the sign convention properly, we always measure Y upwards. So that would actually be a minus value there, and the bending moment is minus. So the two minuses there would cancel out. But anyway, the answer is 40 by 2 by 108. 48.3 pascals in tension. Okay, just as a matter of interest, the bottom stress would be, again, it's 40 to the 6. This time the Y value is this guy here, 128.57. and that's a minus, and it's a plus, divided by 108. And that is so it's 40. Should be very close. $47.2. Okay, so because the centroid is nearly in the middle, the values of stress at the top and bottom surfaces are nearly the same. Okay, so so really the thing to take away from that is that it's just there's a methodical way to do these things. You know, you probably will be asked to do a hand calculation for the next homework, and that's essentially how you do it. Now I just want to try and bring something up here. Can one little second.